everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And in today's topic, we will see the definition terminology discussion on the module 5, which is finite volume method. So in the previous sessions, we have seen the definition terminology for the module 1, so which is based on the Navier-Stokes equation, which is derived with the control volume fixed in space, moving with space. And in the second module, we have seen basics of the PDE, where we have discussed about the elliptic, parabolic, and hyperbolic equation. And in the third module, we have seen basics about the explicit and implicit approach, and we have differentiated them using the Taylor series of expansion. Then in the fourth module, we have seen the basics of the discretization, where we have seen the CFL number, so the significance of the CFL number on the numerical simulation we have seen. And in today's module, we'll see the fifth one, so where we will discuss about finite volume method. So here the finite volume method definition terminology question is, so basically how do you correlate the convection and diffusion equation actually. So where do we have the convection and diffusion equation, and how do you see what is the approach that you use finite volume method for the convection diffusion equation. So here for the convection diffusion equation, so we actually have to concentrate initially on the single terms, where we need to see the convection term and we need to see the diffusion term. Then we have to concatenate or the club the combination of convection and diffusion. So here basically rho into u. So basically this rho into u, basically we say it as convective flux actually. So in the momentum equation, so you have the convection term and we have the diffusion term. So if you see the continuity equation, so we have dou rho by dou t plus del dot rho v bar equal to 0. So this is the continuity equation which we have. So for this continuity equation, so basically there is nothing like a convection term, but whereas if you see the momentum equation, so from the Navier-Stokes equation, basic thing, F is equal to m into A. So F here the forces are divided into two categories, so which is body force and the surface force. So we have two types of forces which are available. One is like body force, other one is the surface force. So in the body force, so the majority of force is acted throughout the volume with the help of gravity, electromagnetic, and other aspects we have. Surface force, we have the pressure, shear, pressure and shear force. So where here in the surface forces, we have divided into two, where you can say it as normal force and axial force actually. So in the normal force, you can take it as the pressure and the normal stress you can take. So in the axial force, you can take it as the viscous, these aspects. So the force, so basically here in the force terminology, so we have the diffusion term actually. Here m into A, so mass into acceleration. So here for the mass into acceleration, so in A term you have the convection term. So we'll see in detail. So let us take an equation where you have du by dt plus c into dou u by dou x is equal to 0. So this is basically an equation so which states about the convection predominant. So it's a 1D wave equation. So where we are majorly talking about the convection term. So this term which is corresponding to the convection term. So another example for the diffusion is, let's say, you have dou t by dou t plus alpha dou square T by dou x square is equal to 0. So this is a transient, basically unsteady thermal diffusion equation, where so you can see this alpha, basically this terminology so is corresponding to the diffusion term. Now, so what do we have by comparing these two? So one equation, you have the motion of the fluid. Let's say you have axis system. Let's say for the axis system, you take this as x-axis, take this as y-axis, take this as z-axis. So when your fluid is moving along x-axis, so the motion or the convection happens along x-axis, the diffusion phenomena will happen along y and along z-axis. Okay, so the pure examples for the convection diffusion phenomena we can take as let's say you have an smoke which is coming out of the car or bike, you can take, or you can take the smoke which is coming from the industrial chimney, you can take. So what happens? So when this smoke or the flow which is coming out of the industrial chimney, so it will move from one point to other point. So that is called the convection. So let's say it is going along y direction. Okay. So let us take the chimney example. So you have the industry. So where you have this smoke going along the y direction, but it will spread. It will not be there, so it will spread in all the directions. Okay, so initially at the point of leaving the chimney, so it is, let's say, uniform, or let's say unidirectional. Let's say it is along y axis. So when it is going or increasing the distance along y axis, what happens? The diffusion or the spreading of this smoke is happening along x and along z axis. So basically here you can see that, so the convection, if you have, let's say, the convection if you have along one direction, so let's say x axis, the diffusion will happen along y and z axis. Okay, so we can take another non-dimensional parameter, so which you have Reynolds number. So Reynolds number is nothing but so rho v l by mu. So Reynolds number is basically a non-dimensional entity or a non-dimensional number, so which actually specifies the ratio of the inertial force to the viscous force. So inertial force to the viscous force. So the numerator, basically the inertial force is corresponding to the convection term, and the denominator where we have the diffusion term or the viscous force is corresponding to the diffusion actually. So here the Reynolds number is an important non-dimensional parameter which will govern the physics of the flow, or you can say another way where it can give the information about the flow, where how much amount of velocity it has, what is the viscosity of the flow, what is the characteristic length on which it is traveling, and what is the density of the flow. So basically these important significance or these important properties will be discussed by the Reynolds number. Now, so the Reynolds number, you can take it as the ratio of the convection to the diffusion. So you have the low Reynolds number. So Re corresponding to low, where you have high diffusion. So you have high diffusion term. Okay, so if Re is low, if the Reynolds number is low, so you can take it as the diffusion term is very very high. So when the Reynolds number can be low, so in the numerator terms you have density, you have velocity, you have reference length. So if you have low dense fluid, very less dense fluid, so the Reynolds number can be low. If you have very low velocity fluid, the Reynolds number can be low. So if you have low, let's say this reference length, the Reynolds number can be low. So examples of low density fluid, like you can take it as let's say rarefied gases or gases with negligible viscosities. So those things you can take. And low velocity fluids. So low velocity fluids, let's say you have some fluids which will travel at low velocities, that thing, low reference length. Now high viscous fluids. So high viscous fluids, example you can take it as, let's say you have honey. So honey is a high viscous fluid, or you can take any gel kind of thing that is in high viscous fluid. So basically, an example you can take, a realistic example. So you can swim easily in water. Let us say you have a swimming pool where you have the water. So while the convection, so basically a swimmer is doing is swimming such a way that he has the convection phenomena where he will head towards certain direction with certain velocity. So it has some diffusion also, where there you have the combination of convection and diffusion. Now the same swimmer, if he wants to, let's say you have a honey tank, so if he wants to swim in honey, so it is very hectic or difficult task. Why? Because the viscous force is very high, therefore the convection term is reduced, diffusion term is increased. Okay, so that is the example of the low Reynolds number. So combination of convection and diffusion for the low Reynolds number we have seen. Now when Re is equal to high, for high Reynolds number, what happens actually? So the convection term will be high. So high Reynolds number in the sense, so your viscous force is low. So viscous force low in the sense the mu term is low. Okay, and rho VL term will be high. So the numerator will be high and the denominator will be low. So examples we can take. So you can take an example of the water tank. Okay, so or a water. So where a person running in the water, so will have certain velocity. A person running in the same tank without water will have certain velocity. Why? Because so here water is a viscous fluid, so where it will offer the resistance, which is nothing but the drag, so to the body which is moving through it actually with that. Okay, so what happens actually? So when a person tries to run in the water, so a friction or a resistance is offered by the fluid medium. Now the same person is running in the tank without water, so he'll have high velocity, in the sense high convection. So why high convection in the sense what? So more convective convection phenomena will be there. So let's say you have Fc convective force, Fd diffusive force. Okay, so convective force to diffusive force. So basically this ratio. So if the convective force is high, so the diffusive force will become, let's say, low. Okay, so the realistic example which we have discussed is, let's say a person who is traveling in the water tank. So where he is running with high velocity, which in turn we can say that so the diffusion phenomena or the viscous phenomena is reducing the velocity. So the same person, he is running without water, so you will have high convection, low diffusion. So therefore you have so more amount of convection velocity. So this is an example. Okay. Now coming back to the Navier-Stokes equation. So having this knowledge, so when you non-dimensionalize it, so we have the Reynolds number as a part of equation in the momentum. So non-dimensional in the sense what? So we have general, let's say you have the momentum equation, which is dou u by dou t. So first term is corresponding to the unsteady term, or the you can say is the local derivative term, plus let's say v dot del u. Okay, so v dot del u. So basically here the first term is called the local derivative, and this second term is called the convective derivative. Or first term you can take that local acceleration, Second term you can take it as convection acceleration. The meaning is, you take a fluid particle, so you have x, you have y, we have z. So a fluid particle is present, it has to go from here to somewhere here. Okay, so at time t is equal to 1, at time t is equal to 2. So when it is going between time t is equal to 1 and 2, so the first term will give you at every instant. So what is the acceleration of the fluid particle? Okay, so it is called the local acceleration. So at this instant, if you want to calculate, at this instant, if you want to calculate, at this instant, if you want to calculate, so this information is provided there. Now the second term will give us the information about the acceleration with respect to space. So when it is moving from, let's say, path A to B, so with respect to this part, what is the acceleration associated with respect to the space coordinates will be given. Okay, so this term is basically giving, information about the total acceleration of the fluid particle. So which we can say it as dou u by dou t. So we can say this one as a material derivative or the total derivative. So total derivative, material derivative, or the substantial derivative is the combination of the local derivative plus the convective derivative. Fine, which is equal to minus 1 by rho. So this equation we are writing it for incompressible flow. When the flow is compressible, so we have rho here, we will have rho here inside these equations, which are terms which are present on the left hand side. Okay, 1 by rho, so dou p by dou x. Okay, dou p by dou x. So this first term is corresponding to the pressure gradient term, plus you have mu square into dou square u by dou x square plus dou square u by dou y square. Okay, so if you don't have any body force term, that will be 0 here. Fine, so this is basically the diffusion term. So this is the convection term. Okay, so when you are performing the, let's say, numerical analysis, or when you are doing the numerical simulations, so the convective term and the diffusion term, so their combination has to be treated properly. Why? Because when you are integrating or when you are combining both, you cannot use both same scheme. Okay, so we cannot use both the same scheme. Why? Because the convection term has a non-linear term actually. So basically, if you see here, let's say you have u into, let's say, dou u by dou x, something like this. So this is a non-linear entity. So the non-linear entity is quite different from the second order term. Okay, so when we see the finite difference formulation for the dou square u by dou x square, we can directly write down the FDE method, like FDM method, to discretize or to make it in linear form, or let's say in finite volume method we can replace this. But for the non-linear term, so we have to actually linearize them and perform the discretization approach. Okay, so that's why, so when you see the convective term and when you see the diffusion term, so these two terms are very different actually, and very different in the sense you cannot relate, or let's say you cannot use the both same scheme. Fine, so therefore, so on the left hand side you have let's say convective force, on the right side you have the diffusion force. So when the fluid is traveling, or when the fluid element is traveling from one place to other place, so the balance between the convective and diffusion will happen. So balance between convection and diffusion in the sense, so when it is going from station 1 to station 2, so let's say in this way, what is happening is, so if the convection term or the FC is decreasing, the diffusion term will increase, FD will increase. So at each and every point in the path between 1 and 2, your diffusion and convection forces are to be balanced. Balanced in the sense they are should be taken properly into account. So you cannot neglect one diffusion, or let's say you cannot neglect convection term. Every time when fluid is going from one point to other point, you will have the convective force, you will have the diffusive force. So I will give an examples. I'll give examples where for the low speed flow or the low Mach numbers, or let's say subsonic, okay, low subsonic Mach numbers. So what happens? You have diffusive force very high. Why? Because how, like, let's say you have Reynolds number, so which is rho v L by mu. You have Mach number, so which is v by a. So what is v? Let's say velocity of the fluid or velocity of the object. So here we use that one. So if the velocity of the reference fluid or the, let's say, object is less, what happens? Ultimately, the Reynolds number also will become low. So what happens actually? So when the Reynolds number and Mach number is becoming low, so the convective force is becoming less. Therefore, the diffusive force is becoming high. Okay. So this is the case. So the other case, you can take the hypersonic or supersonic flows where the convection is very, very high, the diffusion is low. So the boundary layer is very, very small and attached near to the body. Okay. So therefore, here the diffusion is very less. Okay. So this is an example where let's say you have, like we have seen the high Reynolds number and low Reynolds number, high Mach number, low Mach number to discuss. So basically, if Mach number is high, so let's say Reynolds number will be high and the FC will be high. So this is the case. And if the Mach number is low, the Reynolds number is low, so FC will be low. So this is the case you have. The other case you can see, the Mach number is low, if Reynolds number is low, so your FD will be high. Okay, so these are the possibilities which we have. Why we are discussing Mach number and Reynolds number? Why? Because so these non-dimensional parameters, are available when you non-dimensionalize this equation. Okay, when we non-dimensionalize this equation, non-dimensional in the sense this velocity u by u reference velocity, so t by reference time, so pressure by reference pressure, so x by reference length. So when we do these aspects, okay, so when we do these aspects at the end here, you will get divided by RE. So this term will go off. So like this, it will become 1 by RE. So the dependency of Reynolds number will come. So that is why we are discussing majorly with respect to Reynolds number, which in turn it is correlated with the convective and diffusive flux. Okay. So with this, we have seen the definition terminology, which is the combination of the convective and diffusion terms. Okay, for the module 5. So with that, we conclude the definition terminology discussion for the course computational aerodynamics. So in the next session, we will see the problem solving for the computational aerodynamics course. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.